Okay. Okay. Pak Denny is ready. Okay.
Okay.
Yeah. Yeah. So, good afternoon, everyone. I am Edy Tri Baskoro, and I am your host today for this series. We are delighted to welcome you to our Mathematics Distinguished Lecture Series. And today is the fourth edition of this year's Mathematics Distinguished Lecture Series. We are very grateful to welcome the Dean of the Faculty of Mathematics and Natural Sciences at Institut Teknologi Bandung, Professor Wahyu Sri Kutomo, and we are also thanks him for his continuous support in holding this series. And today we are honored to have Professor Senjo Shimizu in this lecture. She is one of the prominent mathematicians from Japan, and she is a professor of mathematics at Kyoto University, Japan, and she was the president of the Mathematical Society of Japan 2021 up to 2023. And she received several awards, and one of them is 2014 Friedrich Wilhelm Bessel Research Award from Alexander von Humboldt Foundation, Germany, and 2 awards from Japan. And in this today's lecture, Professor Shimizu will discuss about free boundary problems for the Navier-Stokes equations. And the talk will be chaired by Dr. Denny Ivanal Hakem. And I would like to mention here that the audience is not only from Indonesia, usually, but also from the neighboring countries. The Mathematics Distinguished Lecture Series is organized by the Department of Mathematics, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung. And now I will invite Professor Wahyu Sri Kutomo, the Dean of the Faculty of Mathematics and Natural Sciences, to give a welcoming remark. Professor Wahyu, time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Thank you very much, Pak Edy. Ladies and gentlemen, all the faculty members, students, and all the distinguished guests, thank you very much. And good afternoon. And also welcome to the 2023 Mathematics Distinguished Lecture Series at the Institut Teknologi Bandung. As we heard from Professor Edy, today marks the 4th installment of our lecture series. And we are honored to have with us a distinguished speaker, Professor Senjo Shimizu from Kyoto University, Japan. Professor Shimizu is a renowned expert in the field of mathematics, particularly in the study of free boundary problems for the Navier-Stokes equation. Her groundbreaking work has contributed significantly to our understanding of fluid dynamics and the mathematical challenges posed by free boundary phenomena. And of course, on behalf of the Faculty of Mathematics and Natural Sciences, I hope that this lecture today promises to be intellectually stimulating, offering insight into complex mathematical models that govern the behavior of fluid flows, with a particular focus on the intriguing Navier-Stokes equation. Her expertise and depth of knowledge in this area will undoubtedly provide a valuable perspective for our researchers, to all of us, particularly our young researchers and also students and enthusiasts alike. Once again, I hope that all of us can enjoy this lecture and obtain benefits from the discussion and also from the sharing knowledge that will take place today. Once again, thank you very much to Professor Shimizu and to Professor Edy for making this mathematics distinguished lecture continues to go on. And I hope once again we will have a good discussion and enlightenment. Thank you very much, Pak Edy. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you and terima kasih Professor Wahyu for the welcoming speech. And now I would like to transfer our control to Dr. Denny to chair this lecture.
Okay, thank you, Pak Edy. Before that, we would like to take a group photo. So there are 2 pages here. I will count from 1 until 3 for the first pages. So kindly turn on your camera in Zoom. So I will count. I will wait for a moment till please turn on your camera. Okay, so this is for the first page. Okay. Okay, I will start just a moment. We'll start the counting from 1, 2, and 3. Okay, so this is the first page, and we continue to the second page. Let's prepare the camera, and then our count 1, 2, 3. So okay, that's about it. Okay, so the group photo is taken now. Just a moment. Okay, so you may. Okay, so now I'd like to chair this session. So first of all, thanks Professor Shimizu for being the speaker for this mathematics distinguished lecture series. So I would like to give a few announcements and then read the CV of Professor Senjo Shimizu. Just a moment. Just a moment. Okay, that's about it. Okay, so yeah, I will use the slideshow. Oops. All right, so ITB Mathematics Distinguished Lecture Series 2023. This time the speaker is Professor Senjo Shimizu from Kyoto University. So before reading the CV of Professor Senjo Shimizu, there are a few announcements. First, please mute your microphone at all time in Zoom. And then for the Q&A, question and answer, please write your question in the chat section of Zoom, in comments in YouTube. And then I will read your questions, select if necessary for the speaker to answer. And then the audience in Zoom will be allowed a few selected short questions to be asked directly during question and answer. And please raise hands first until I will point you to unmute and ask. And this is the brief schedule. We have an opening and then an hour lecture, a short break before question and answer, and then the closing remark. Okay, so I will continue to the CV of Professor Senjo Shimizu. Professor Senjo Shimizu obtained her master degree and doctoral degree from University of Tsukuba in 1991 and 1994. And after that, she became a lecturer at Shizuoka University until rank of professor in 2008 until 2014. And after that, she became Humboldt-based researcher in University of Halle-Wittenberg in Germany. And then she became the professor at the Graduate School of Human and Environmental Studies in Kyoto University from 2015 until 2022. And from this year, she became the professor at Department of Mathematics, Kyoto University. And she, as mentioned by Edy before, she obtained several awards, among other 2014 Friedrich Wilhelm Bessel Research Award from Alexander von Humboldt Foundation, and before that, the Degree of Excellence Researcher in 2013 from Shizuoka University, as well as Fukuhara Prize in 2012 from Division of Functional Equation, Mathematical Society of Japan. And among other, previously, she was the president of the Mathematical Society of Japan, and also a member of Mathematical Society of Japan Executive Committee, as well as the member of International Mathematical Union General Assembly on this occasion, as well as the member of Selection Committee of King Faisal Prize in Science in Saudi Arabia. And here are the selected 5 publications, and the recent one is maximal L1 regularity and free boundary problems for incompressible Navier-Stokes equation in critical space. And without further ado, I would like to invite Professor Shimizu to give her talk titled Free Boundary Problems for the Navier-Stokes equation. So please share your screen and start the lecture, please. Thank you.
Dr. Denny, thank you very much for your precise introduction. First of all, I'd like to thank Professor Edy Baskoro for giving me occasion to have a talk in Mathematics Distinguished Lecture Series supported by Institut Teknologi Bandung. Today, I'd like to talk about free boundary problems for the Navier-Stokes equations. Let the region omega of t occupied by the fluid be given only on the initial time t equals 0, while for a positive t, it is to be determined. We take positive direction of yn downwards, just like living in southern hemisphere. Eta bar vanishes at t equals 0.
Sorry, Professor Shimizu, the slide is still not moving.
Slide?
Yeah.
Moving.
Still not, yeah.
It's still in the first page. And you move to the
really?
second one.
Oh,
yes.
So, okay. So, excuse me. So,
yeah.
Is it possible to see like this?
Yeah, now,
okay.
Now it's
okay, okay.
Yeah, we can see the equation now.
Okay.
Thank you.
Very excuse me. And can you see this hand mark? Okay.
Yes.
So, now I start again. Excuse me. Yeah. Let the region omega sub t occupied by the fluid be given only on the initial time t equals 0, while for a positive t, it is to be determined. We take positive direction of yn downwards, just like living in the southern hemisphere. Eta bar vanishes at t equals 0. So the initial region omega of 0 is the Hauss space Rn plus. Let an initial velocity u0 bar be given. We consider the problem to find a domain omega sub t for a positive time t and to find the velocity vector u bar of ty and pressure p bar of ty, satisfying the Navier-Stokes equations. The first equation describes the conservation of momentum. Here, capital T is the stress tensor given by the symmetric part of gradient of u bar minus p bar. Here, capital I is the identity matrix. The second equation shows conservation of mass. The divergence-free condition means the fluid is incompressible. Under the divergence-free condition, divergence of stress tensor capital T is equal to Laplacian u bar minus gradient p bar. On the free boundary, d omega of t, two conditions are imposed. One is dynamical condition, which expresses the balance of forces at the free boundary, such that the normal direction of the stress tensor vanishes. The other one is the kinematic boundary condition, which tells us the speed of the evolution of the free boundary in the normal direction coincides with the normal velocity. I call this problem FNS as abbreviation of free boundary problems of the Navier-Stokes equations. First, we transform free boundary problem into fixed boundary problems by using Lagrangian transformation. Since Solonikov used the method, Lagrangian transform is frequently used for changing a free boundary into a fixed boundary. Eulerian coordinates y is given by the solution of the ordinary differential equation with initial value x is Lagrangian coordinates. The solution y is given by this time integral equation. We set u of tx, u bar ty, p of tx equals p bar ty, and eta tx equals eta bar of ty prime. By the derivative of the composite function, the time derivative of the boundary function eta equals dt eta bar plus in the product of u bar prime and gradient prime of eta bar. and it is equal to UN bar by the kinematic condition. Integrating both sides, eta tx is equal to eta bar ty, and it is given by the integral of UN bar, and this is equal to, by this equation, yn minus xn. This means eta bar minus yn equals minus xn, and here eta bar minus xn is negative, so minus xn is negative. This means the kinematic condition ensures that the Lagrangian coordinates xn satisfies always positive, namely x belongs to Rn plus. In this way, the time-dependent omega of t is changed into fixed domain Rn plus. As we see, the boundary function eta has disappeared in the Lagrangian transform. Only unknown is u of tx and p of tx. We denote the Jacobi matrix dy dx by j of du, whose ij component is given by this equation. It is equal to Dirac delta ij plus time integral of dui dxj. Jacobi matrix J of du has a good property such that its determinant is equal to 1 because you satisfy the divergence-free condition. Therefore, transposed inverse matrix of J of du equals the cofactor of J of du. This is the Lagrangian transformed problem of original free boundary Navier-Stokes equations. Here, the identity minus inverse matrix of Jacobi matrix it is given by the n-1 order of polynomial of the time integral of the first derivative of the velocity. Because n1 and 1 determinant. And in the first term, 2n minus 2 order of polynomials of the time integral of the first derivative of the velocity is multiplied by the second derivative of u. In this way, all nonlinear terms F, capital G, and capital H are quadrilinear terms, where their coefficients are polynomials of multi-products of time integral of the first derivative of the velocity. I call this Lagrangian transformed problem TNS transformed Navier-Stokes equations. We are now getting away for the free boundary issue. Let us look the Cauchy problem for the original Navier-Stokes equations in the whole space. The Navier-Stokes equations are the semi-linear equations, which contains nonlinear term v dot gradient v. We introduce the Helmholtz decomposition. LQ space is the direct sum of LQ sigma and GQ, where LQ sigma is divergence free space completed by LQ norm, and GQ is the space of gradient of pi. We decompose the function f belongs to LQ as f equals g plus gradient of theta, where g belongs to LQ sigma and gradient of theta belongs to GQ, and set solenoidal projection P F equals G. Solenoidal projection means only the divergence free space. Applying the solenoidal projection P in the first Cauchy problem, then it changes into this problem. Here, minus P Laplacian, I set it is equal to capital A. And the domain of dA is equal to W2Q intersection LQ sigma. This capital A is called the Stokes operator. Now we set U equals solenoidal projection operated by V. Then this equation can be expressed by this equation. The solution formula of this equation is obtained by using Stokes semigroup exponential minus TA U naught minus the time integral of this term. Now we take the space. This semi-linear equation has the solution. I set capital X like this. For PB greater than N, U belongs to Ln sigma in space and bounded continuous in space, LP sigma in space and bounded continuous in space with weight T to the power n over 2 times 1 over n minus 1 over p. And time weight t to the power 1/2 gradient of u belongs to ln sigma in space and bounded continuous in time. Essentially, this is the essential part. So I consider gradient of u. For the first time, u1, it is easily obtained that p in this LPLQ estimate, we take p equals q equals n, then we obtain t to the power 1/2 gradient of u1 belongs to this class. So we check gradient of u2. The ln norm of this u2 is estimated by using LPLQ estimate. Here p take q and n take, here q take n, we obtain this estimate. Next, here, using this relation, t to the power n over 2, 1 over n minus p1, 1 over p here, and here, s to the power 1/2 here, and getting out, taking supremum of time. Then, by using this relation, the remaining part can be used by using function beta 1/2 minus n over 2p, n over 2p times t to the power minus 1/2. Here, p is greater than n. Both are positive. So, we can obtain u2 belongs to this class. In this way, for a semilinear equation, only we consider the first derivative. So LPSQ estimate of Stokes semi-group is works. On the other hand, if we consider quasi-linear equations, by using Duhamel principle, the solution formula is obtained like this. It is no problem. But consider the second derivative of u. If we again use LPLQ estimate of Stokes semigroup, then here, P minus S inverse comes. It is a problem because S equals to T. This minus 1 is singularity. It is not integral. In this way, for quasi-linear equations, semigroup approach doesn't work well. For quasi-linear equations, the alternative to the semigroup approach is maximal regularity. let capital X be a Banach space and capital A be a generator of analytic semigroup on capital X. And we consider the abstract ordinary differential equation. We say that capital A has maximal LR regularity if for a given F belongs to X valued LR in time, where capital I is time interval. The time derivative of U and A operated U of LR X norm can be estimated from above by initial data U naught. Its norm is real interpolation factor between X and D of A between 1 minus 1 over R and R, plus the external force S, LR IX norm. In view of analytic semigroup theory, if the external force F belongs to C theta, theta is theta order Hilda continuous function, then there is a solution of 1, the time derivative of U and AU belong to X valued continuous in space. In the semigroup setting, the time regularity of F is theta order higher than time derivative of U and AU. But maximal LR regularity has the same regularity between F and time derivative of U and AU. Just same LR. Therefore, it is called maximal LR regularity. Maximal LR regularity resolves the singularity A multiplied Stokes semigroup e to the power minus TA almost 1 over t as t goes to 0. Namely, LR norm of AU is here 1 over t convolution F, but it can be estimated from above by LR norm of F. The theory of maximal regularity has been established for R between 1 and infinity, but excluded 1 and infinity, and for a UMD Banach spaces of capital X. UMD is unconditional martingale difference Banach space. Roughly speaking, it is a reflexive Banach space. This theory was here only restricted name, the Plato-Grisbard, Dore, Amann, Weiss, Genkheber plus. Indeed, if we use maximal LR regularity for the linear problem, we can construct the solution in the complete metric space capital X as follows. Given V belongs to X, we consider the linear problem. We consider the map from V to U by the suitable nonlinear estimates the capital phi of V can be estimated from above by this initial norm and here the quantity of M. So if we take constant times the sum of Mk is less than 1/2 and constant times U0 norm is less than M/2, capital phi is a contraction map. By the Banach fixed point theorem, we know that there exists a unique fixed point of U of the map capital phi in the space X. Now we return to free boundary problem. Free boundary problem is one of the classical important problems for the Navier-Stokes equations. In the list, only restricted works are cited. There are many other references. For a drop problem, a bounded domain, pioneers' works were done by Solonikov, and then global well-posedness or stability were obtained in these function spaces. Here, W21P is the space R is equal to P. This is just maximal LP regularity space. Free boundary problems become quasi-linear equations by transforming a free boundary to a fixed boundary. For this reason, the study of free boundary problem is closely related to the development of the study of maximal LP regularity. For an ocean problem with bottom, infinite layer of finite depths, just like the picture, pioneers' works were done by Beale. Local and global well-posedness are obtained. For ocean problems without bottom, Simone and myself obtained local well-posedness for two-phase problem. Today's problem is corresponding this ocean problems without bottom. This is not bounded domain or not finite depth. So we don't use Poincare inequality. It is difficult to obtain global well-posedness. The exterior domain, Shibata obtained global well-posedness. Well, let us consider the scaling invariant space for the Navier-Stokes equations. The Navier-Stokes equations have the parabolic scale lambda squared t and lambda y. And from the balance of linear terms and the nonlinear convection term, lambda and lambda squared are multiplied by the velocity u bar and the pressure P bar, respectively. If U bar and P bar are the solutions of the Navier-Stokes equations, then U sub lambda bar and P sub lambda are the solutions of the Navier-Stokes equations. Under this scaling, We know that error in time and the homogeneous vessel potential space H dot SP in space with 2 over R plus N over P equals 1 plus S are the scale invariant spaces. For free boundary problems, previous results were obtained on W21 PR space, where R is greater than 2 and P is greater than N, because by using this embedding relation, so it seems to be difficult to solve in a critical space in the previous Sobolev space setting. If we choose R is infinity, then S is naturally negative 1 plus N over P. And if we take R equals 1, then S is equal to 1 plus N over P. This space, now we use this space. Here, B dot SP1 is included in H dot SP and has the same scale, but more small space. So B dot minus 1, this B dot minus 1 plus N over B P1 means minus 1 plus N over P is differentiability, lower left P is integrability, and lower right 1 is interpolation index. We'd like to consider global in-time existence of FNS or TNS in the scale critical space. Global well-posedness results in scaling invariant class was obtained by Danshan, Hiba, Muha, Toruk-Stolf, and Ogawa, myself. Before stating our results, we define the homogeneous vessel space and the homogeneous Rizolkin trivial space. Let phi be Rizolto-Perez direct decomposition for space variable x. The homogeneous vessel space B dot SP sigma of F tilde is first take LP norm phi convolution F tilde and then take small L sigma norm with weight 2 to the power S J. In the half space Rn plus, we take infimum of F tilde in the whole space for Xn is equal to F and negative Xn a proper extension. Capital CK be the Rizolto-Perez direct decomposition for time. The homogeneous Rizolkin space F dot SP sigma first take small L sigma norm. And then after taking LP norm. And for in the half line R plus, we take infimum of whole line norm. For positive T, it is equal to F and negative T a proper extension. This is our main result. This is obtained by Professor Ogawa in Tohoku University. Let n is greater than or equal to 2. P is greater than n-1 and less than n-1. If the initial data you note is sufficiently small, then transformed problem admits a unique global solution such that U belongs to scaling critical continuous in time with values homogeneous vector space B dot minus 1 plus n over p p1, and U and P belongs to maximal L1 regularity space. And the pressure itself on the boundary has this additional regularity. And the solution is uniformly bounded. In the result, we can take P is greater than N. This means we can catch the solution belongs to the negative order regularity. By theorem 1, we know that the first derivative of U belongs to L1 with values in B dot n over P P1. The homogeneous space B dot n over P1 is embedded into CV, where CV denotes continuous function with asymptotically flat. This shows U is the Lipschitz continuous function for almost all time. Therefore, the ordinary differential equation solves uniquely global in time. So, as a corollary of theorem 1, we obtain the following. The same assumption as in theorem 1, and let UP be the global solution of transformed problem obtained in theorem 1. Then the pullback U bar P bar of UP satisfies original free boundary problems. Denk, Heber, Muha, Tolksdorf obtained similar results. Their results were based on beautiful Daplat-Grisbard theory, obtaining maximal L1 regularity for the Stokes equations, which is completely different method from ours. However, the range of P is restricted up to N. Now, we would like to show a key part of the proof. The key theorem is maximal L1 regularity for the Stokes system in the House space with stress boundary condition with non-homogeneous data. As I mentioned, if we consider maximal LR regularity for L is greater than 1 or less than infinity, it is well studied, and there are good general theory. But for L1, the maximal L1 regularity, there is no well-established theory. So we obtain our method. The result is the following. Let P be 1 and infinity. The regularity S is greater than -1 plus 1 over P and less than 1 over P. There uniquely exists the solution UP to the Stokes problem S. Where the regularity U and P belong to this regularity, and the pressure on the boundary has additional regularity, as we see in the main theorem, theorem 1. The nonlinear problem and linear problem is the same regularity class. And this maximal L1 regularity was a Stokes equation. The data F, G, H, and U naught belong to this class. This is obtained if and only if the maximal L1 regularity and also maximal LR regularity are obtained by Solonikov, Denkiva Plus, Shibata myself, Danshan Muha, and plus Shimone. In order to obtain maximal L1 regularity, we introduce polyunfilled arch type of Littlewood-Perret dyadic decomposition. This is direct product type. The support of magenta part and yellow part are illustrated like this. Thanks to this new polyunfilled type, arch type, Littlewood-Perret dyadic decomposition, we can treat modulus Xi prime and Xi n independently. We use the explicit expression formula of the pressure obtained by Shibata and myself. Here, the pressure P is Cp convolution H. Actually, this Cp is explicit formula. And then we take B dot SP1 norm by using this capital phi and divided this norm, magenta part and yellow part. Next, we split the data H into the time-dominated region and the space-dominated region. K is greater than 2J. Here is time-dominated region, and K is less than 2J. This is blue region. It's the space-dominated region. So we would like to obtain L1 in time, B dot S P1 in space of gradient P. So L1 of magenta part and yellow part. Now we consider magenta part. The data H is decomposed into the time-dominated region and the space-dominated region. This LP norm of X prime, we use Young inequality. And so here, taking L1 and rest, we take LP. The L1 norm part of X prime is here. We use almost orthogonality property. For time-dominated region, the almost orthogonality means time t and xn. For a space-dominated region, if k is less than 2m, then the almost orthogonality is xn and x prime. Now, we consider only time-dominated region. The L1 norm of here, taking L1 norm here, using this inequality. Then here, 2 to the power m comes here. And here, we take change of variable, 2 to the power mxn equals yn. Then here, 1 over p. So this means 2 to the power minus m over p comes from this variable. Now we consider time-dominated region, namely k is greater than 2m. So the red term is changed into k over 2 times 1 minus 1p. So we obtain homogeneous resolving trivial space. The regularity 1/2 minus 1 over 2p. And this is, in the definition, it is equal to this regularity of the boundary data H. This means for this boundary data, now we obtain gradient P belongs to this space. Other terms, as in a similar way, we obtain this. More precisely, for F and G, we use, first we use the whole space problem and eliminate the data. Also, you know that also. So it is the point that only H remaining problem. Now we consider that problem. So if we obtain maximal L1 regularity, so finally, we use contraction mapping principle in the complete metric space capital X. U and P belongs to this maximal L1 regularity class, and the boundary pressure also belongs to this class. The X norm of UP take like this. And first, it is less than capital M. Given V and Q belongs to X, we consider the linear inhomogeneous initial boundary value problem or the transposed problem. We consider the map from the data VQ into UP. Then UP, namely capital phi of VQ, is with suitable nonlinear estimate. It is estimated from above by this initial norm and sum of m to the power k plus 1. Here, k equals 1 to n minus 2. If we can take constant c times m to the power k, sum of k equals 1 to 2n minus 1 is less than 1/2, and the constant c times this norm of u naught less than m over 2, then this is less than capital M. This means the capital map, capital phi, is a contraction. So, by using the Banach fixed point theorem, we obtain unique existence of nonlinear transformed problem. That is all of my talk. Thank you very much for your attention.
Thank you, Professor Senjo Shimizu, for your nice lecture. And it's a really nice result in the recent publication with your co-author, I think. Yeah, before we go into the question and answer session, we will have a short break and music performance usually. And I will give the control to the Edy, Professor Edy Tri Baskoro. Please.
Okay, thank you, Pak Denny. And thanks for very nice and inspiring lecture from Professor Shimizu. And as I promised earlier, we will have a performance, musical performance. And this time we will present angklung performance. As we know that angklung is a musical instrument from Sundanese people in Indonesia. And this instrument made by bamboo. So, okay, so let's now listen to the performance of angklung. Okay. Okay, the title of the song is Radabi.
We are thousands miles from comfort. We have traveled and seen. But as long as you are with me, there's no place I'd rather be. I would wait forever, exalted in the sea. As long as I am with you, my heart continues to be. Wherever step between Kyoto to Beijing, so casually. I'd rather be. We set out on a mission to find our inner peace, make it everlasting, so nothing's incomplete. It's easy being with you, sacred simplicity. As long as we're together, there's no place I'd rather be. With every step we take, Kyoto to the base, falling so casually. We're different than the same, gave you another name, switch off the battery. If you gave me a change, it's a shot in the dark. Knowing the love of your heart, you when I am with you, there's no place I'd rather be. No, 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 no place I'd rather be. No, 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 no place I'd rather be. No, 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 no place I'd rather be. When I am with you, there's no place I'd rather be. Oh, beep, 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 beep.
Okay. Okay, I hope you enjoy the performance. So this performance actually done by our student, ITB students, Professor Shimizu. Okay, now back to Danny.
Okay, thank you, Edy. Yeah, once again, we'd like to open the question and answer session. So there are two questions from Pak Yudi and Pak Agus, and if possible, if you can unmute yourself, Pak Yudi, if you want to ask directly first, please.
All right.
Yes. Thank you, Shimizu Sensei, for the beautiful lectures. The Navier-Stokes is difficult, and make it free boundary is doubly difficult. My question is about this one, actually, the LR regularity. You have some, you decompose the space to some interpolated Lebesgue space, and then UMD, because that's the first time I heard about UMD Banach space. Can you explain a little bit what's the UMD Banach space? Does unconditional martingales have something to do with that?
Yes,
Yes, thank you.
UMD is unconditional martingale differences space.
Okay.
Yeah, and this is roughly speaking. This is roughly speaking. Excuse me, I forgot the English.
Okay.
Reflexible space, namely LP space without L1 and L infinity, UMD space. And it's interpolation space is also UMD space. So UMD Banach space means almost reflexible space. So base space X is reflexible, and the LR regularity LR is also between 1 and infinity. The theory was almost completely the theory was has been studied. And excuse me, what your question again? Excuse me.
That's about UMD space actually.
Okay. So if you use Professor Aman's book in 1995, or recently, it's a very good book. So this book, Analysis in Banach Space, can you see it?
Yeah. Yes.
This is no. No.
Yeah.
Aman, yes, this Aman.
This is another book by Huttenen, Van Neven, Ferrer, and Lutzweiss. 4 people wrote a book. It is a very precise book. And if you see this book, UMD Banach space is expressed in this book.
Okay. Thank you, Sensei.
Thank you, Professor Shimizu, for your answer to the question. And then the second question from
Bagus Yade.
If you can unmute yourself, Pak Agus. Cannot unmute, then I will read the question.
Yes, I can.
No, I will read it for you.
Okay.
So the first question, for the free boundary problem in fluid transformation of equation from Euler description into the Lagrangian description is first applied. Is there any reason to do that? And in general, is it always doing that information is guaranteed? And the second question, maximal LR regularity resolves the singularity. What does the singularity here mean? And where does this singularity take place?
Okay. For the first,
for example, in the
okay.
Problem maybe?
Yes.
May I answer?
Yes,
Yeah?
sure. You can
Okay.
answer the question.
For the rigorous mathematical proof, as far as I know, first this time-dependent region into fixed region. But not only using Lagrangian transform. For example, Bill use Bill transform, and plus Simone or Kone plus Bilk use Hanzawa transform. Not only Lagrangian transform, but as I said, as far as I know, for the mathematical rigorous proof, we change the moving boundary to the fixed boundary. But it is only I know. So in future, there will be no fixed boundary, no fixed no exchange. The fixed boundary is may be proved. And the next question, concerning the next question. So here, t minus s minus 1 comes. So the singularity means the integral diverges. So minus 1 is threshold. If less than 1, it can be, it can, this is integrability. But here minus 1 arises. The integral diverges. This is the meaning of the singularity.
Okay. Okay. So yes, thank you for your answer, Professor Shimizu. Are there any other questions from the participants? All right. Pak Yudi, yes. Please unmute yourself.
Sorry, still muted. Sorry.
Yes,
It's in the more elementary studies of the Navier-Stokes, we use a lot of the Galerkin projection method. And is there any place for still a Galerkin method in these free boundary problems?
Yeah. For other problem, I saw Galerkin method, but for free boundary problem, I have never seen Galerkin method to obtain the solution.
Okay, thank you.
And so you do you use Galerkin method to obtain some solvability?
Yes, I remember this long time ago when I learned Navier-Stokes, and that's more in traditional thing. That's there's a lot of the projections, Galerkin projections, so that's ticking limits, those kind of stuff.
Okay.
Okay.
Okay. Are there any questions? Is there any question? Remark, comments so far? Okay. Probably I will ask several questions, Professor Shimizu. So, related to the Helmholtz decomposition, it's written only words for Q is greater than 1. And what happened to the case when Q equals its weak type? That's for, yeah.
So here, if Q equals 1,
Yes.
the projection does not bounded.
Okay. So that's the restriction.
Yes. So
Okay.
infinity also, Q equals infinity also does not bounded.
Okay. Yeah.
So we exclude bound infinity here.
Okay. Thank you. And the next question, yeah, probably for the related again to the function space. In your result, you consider the homogeneous Disov or triply circle space. Is it relevant to consider the related inhomogeneous one, or is it the equivalent, or
Okay.
it of range? Yes.
If we consider inhomogeneous Besov space,
yes,
then first the scaling is destroyed.
Ah, okay. So there is a problem with the scaling invariant.
Yeah.
Okay, thank you. And for the technique of this one is surprisingly the choice of L1 regularity. So as you mentioned, that is quite difficult for the boundary case, R equals 1, I mean. Is it any thing to do with is it related to the unboundedness of some classical operator in L1, like a Hardy-level maximal operator, or in general maximal operator in L1 is unbounded? Is it related or to the difficulty in maximal L1 regularity?
So, so
Yes.
maximal LR regularity means, Mifilin type,
Ah,
Mifilin type estimate.
mhm.
In some sense, なんだっけ、singular integral operator.
Ah, singular integral.
So Mifflin type inequality R is, so this we can see the X valued LR regularity. So Banach space valued Mifflin type theorem we use. So R is 1 and infinity are excluded.
Ah, okay.
It is the reason.
And yeah, just a follow-up, is it relevant to consider weak type estimates in that case?
Excuse me. So,
with the weak Lebesgue space, or as in the range weak type estimate?
weak type?
Yes, for the case R equals to 1.
Weak type estimate. What's the meaning of weak type estimate?
I mean the R equals to 1, but the norm of the operator is a weak Lebesgue space, L1 infinity, something like that. Is it relevant to consider the case? And then like interpolation or something like
I never think in such a way.
Okay.
So please once again. So small weak type L1 estimate, you mean?
Yes. Yeah, just a guess, because mainly if we work in some classical operators, usually the strong type L1 to L1 does not work usually. L1 to weak L1. I do not know, probably. Yeah.
Okay. You mean L1 infinity? No?
Yes. Yes.
Okay.
Right.
I see. I understand. Okay. First, if we obtain maximal LR regularity, then we can obtain maximal LR infinity regularity.
Yes.
It can be Professor Kozono proved. But so if L1 infinity, if we consider L1 infinity, it is not I never see the result of L1 infinity regularity.
Thank you for your explanation. Maybe Is there any other question in the last 5 minutes of this discussion?
I add the comment.
Sure, you can.
Excuse me. Mifilin type
problem.
means so operator X valued Fourier multiplier theorem. As you know. So in this way, the Mifilin type condition, we check Mifilin type condition. It is only restricted. R is between 1 and infinity.
Ah, okay. Yeah. Okay. Thank you, Professor. Any last question from other audience or the participants? So just waiting for the question. Probably, yeah. Yes, we see that the choice of function space is quite large with 3 parameters, and the difference between Sobolev and Besov probably is negative regularity, right? Difference between Sobolev space and Besov space are in the negative smoothness or negative, as you mentioned. Is that correct? Yes.
This? Yeah.
Yes. With
if
the
it's greater
Sobolev
than-
space. Yes. Yes. Please continue. Sorry.
Yes, if we take P is greater than N, this is negative.
Ah, okay. Yeah. So that's the difference with the Sobolev space.
Yes. So the initial data and also the solution space also -1 plus N over P. So if P take greater than N, less than 2N minus 1, we can take P as like that. Then the space is negative.
Ah, okay. Yes. Yeah, it's perhaps it's the one of the first result in this space. I guess never considered before.
Until now.
Until now, yes.
No.
Yes, after this point. Okay. Yeah, probably there are no more questions. So let's thanks the Professor Senjo Shimizu once again for this nice lecture, and yeah, and also nice discussion a lot about this research or this direction. Yeah, thank you very much, Professor Senjo Shimizu. Arigatou gozaimasu. Yes.
And I'd like to send my thanks for all of you. I'm very fruitful time. I spend a very fruitful time. Thank you very much.
Yes, thank you. So probably for the closing remark, I will give once again control to Professor Edy Tri Baskoro.
Okay, thank you, Danny. And again, allow us to thanks to Professor Shimizu for very nice and inspiring talk lectures in a Saturday, in this Saturday. Usually during Saturday you have holiday time, but this is a very special Saturday. So thanks to Professor Shimizu. And on behalf of the Faculty of Mathematics and Natural Sciences, we would like to present some certificate to Professor Shimizu, and also some small token, small drawing that we try to do it. So let me present the certificates. Later on, we will send you, Professor Shimizu. Okay.
Thank you very much.
So this is the certificate of this Mathematics Distinguished Lecture Series for being a keynote speaker. And we will have one more. Let me. Oh, sorry. No, not that one. Sorry. I couldn't see. Let me. Just a moment. Oh. Here you are. Okay, so this is the. Okay. Oh, sorry. Okay, so this is our thanks to Professor Shimizu for her profound lecture in Mathematics Distinguished Lecture Series. Okay, so we will send you both certificates. Yeah, and again, thank you very much, Professor Shimizu, and also to everybody who attending this lecture. So see you again next year. So we will have Mathematics Distinguished Lecture Series again next year, starting February, probably, yeah. And also, we like to invite you to come to Bandung, Professor Shimizu.
Thank you very much.
If you have time, then we are very happy to have you in Bandung. Okay, so this is the end of this program. And thank you, and Assalamualaikum warahmatullahi wabarakatuh. And see you again next time. Bye-bye. Yeah. Oke, terima kasih semuanya. Thank you.
Terima kasih, Bro.
Ya, terima kasih.
And thank you very much, Professor Edy, Professor Edy, and Dr. Denny.
Terima kasih, Shimizu Sensei. Yeah.
Yeah, tunggu saya, Mas.
See you in Bandung or in Japan, Kyoto. Okay, bye-bye.